Okay, so today we are going to talk about section 2.2, which is graphs of polynomial functions. So far we've only dealt with quadratic functions, but now we're going to get into functions of higher degree. So the first thing we need to focus on is knowing what graph actually represents a function and which kind of graph does not represent a function. So two basic features of the graphs are that of polynomial functions is that the graph is continuous with no breaks, and also that it is smooth and has rounded turns. So that being said, take a look at the four graphs shown here, and I want you to think about which of the following graphs represent polynomial functions. Hopefully you're saying that, let me grab my pen. Hopefully you're saying that A and B are yes functions. C is not because it has a break, and D is not because it has that sharp turn. So when we think about the graph of polynomial functions, when you think about the graph of x squared and of x to the third, they have a certain shape that they're going to follow every time. It may be shifted, it may be a little thinner or wider, but for the most part it follows the same shape. So I want you to think about, will the graph of x to the seventh look more like x squared or x to the third? Hopefully you're saying, well, the exponent here is odd, the exponent here is odd, maybe that has something to do with it, and actually it does. So x to the seventh will look more like x to the third because of the odd degree. And what is a degree again? A degree is the exponent, the largest exponent that you see in a polynomial. Just note that polynomial functions of the form x to the nth are often also referred to as power functions. And power functions of the same power functions of even degrees will have the same kind of end behaviors, and power functions of odd degrees will have kind of the same end behaviors. So let me just fill this in here. This is a power function. All right, so I use that word end behavior, and what I mean by that is as x goes towards negative infinity, what's happening to your graph? Well, the end behavior here is that it's continually increasing, it's going up. As x goes to the right, what's happening to your end behavior? Well, it's going to continue to increase and go up to the right as well. So the end behavior of something like x squared is rising and rising. End behavior here, I'm talking as x approaches negative infinity, my end behavior is going down, and here as x approaches positive values, my x is going up. So in this case, it's going to fall to the left and rise to the right. We're going to talk more about how to identify that in a second. But what I first want to look at is the following functions. I want to know basically f of x equals negative x to the fifth. What do you know about that graph? What can you tell me so far? So I initially had said that all odd power functions have the same end behavior. All even power functions have the same end behavior. So basically I want to know, is this going to look more like x squared or x to the third? This will look similar to x to the third because of that odd. Something else that you should be able to point out and notice is going to change your graph is that negative there. That negative means that it's going to have a reflection. Where is that reflection going to be? Hopefully you're thinking the reflection will be about the x-axis. And that is correct. Oops, sorry, that doesn't look like an x. All right, for B you have x plus 1 raised to the fourth power. So what do you think that's going to look like as far as the end behavior, the arrows on the left and on the right-hand side of the graph? Is it going to continue to increase, continue to decrease, or what? Hopefully you're thinking, well, it's even, so it's going to look similar to x squared, which is in fact correct. Also, something else that you should be able to point out, we have this x plus 1 inside the parentheses, so that identifies a shift. What kind of shift does it identify? It identifies a shift of 1 to the left. All right, so in this section, you should be able to take a look at a polynomial equation and be able to tell me so much about the graph without ever picking up your calculator. And then you should be able to actually graph it without picking up your calculator. So something that we use to help us identify what a picture or what a graph is going to look like is the leading coefficient test. And basically that says as x moves to the left and to the right, as it approaches infinity to the left and to the negative infinity, to the left and positive infinity to the right, it will eventually either rise or fall. So if x is even, meaning if you have something like x squared and a is positive, it should be rising to the right and the left. If you have something like x squared but a is negative, meaning I have a negative out front here, how is that going to change your graph? Well, it's going to reflect the x-axis, meaning that it's going to be decreasing both on the left and on the right. If you have an odd, so if you have something like x cubed and it is positive, remember we talked about that in class, it looks like kind of that tangent function where it has one arrow in each direction. So all odd are going to have one arrow in each direction. So on the left-hand side, it's going to decrease. On the right-hand side, it's going to increase. But if you have an x cubed function and it's negative, it's actually going to flip. It's going to rise on the left and fall on the right. So if I ask you to apply the leading coefficient test, you can basically just give me these arrows, and that's enough to prove that you know what the end behavior is going to look like for a graph. So we have these 3 examples here. I want you to pause the video and take a minute to try them on your own, and then start the video up and I will kind of give you the answers to them. So for the first one, for A, we have a degree that is odd and a leading coefficient that is negative. So that being said, it will rise to the left and fall to the right. For B, your degree is even and your leading coefficient is positive. So it's actually going to rise to the left and rise to the right. And last one, you have a degree that's odd. You have a leading coefficient that is positive. So therefore, it's going to fall to the left and rise to the right. Pretty basic concept. All right, so now let's talk about some more features of an equation that you should be able to apply to your graph. If you can find the zeros of a function, you can basically identify where it's going to cross the x-axis. But what you also should be able to identify is the turning points. The turning points basically tell you where it goes from increasing to decreasing and vice versa. If you can identify the degree of the polynomial, n, that'll tell you the number of turning points. So we're going to use n minus 1 to tell us the number of turning points. And n would be the number of zeros. So for example, if you have x to the 4th, x to the 4th says that you have 4 zeros and you're going to have 3 turning points. Okay, so that's going to just kind of help us identify where we should have points throughout our graph. So this next slide is basically talking about the characteristics if you know that f is a polynomial function and it has a real number a as a 0. Basically, just copy all this down in your notes. It's really self-explanatory. We have seen it written in plenty of forms already. If I say x equals a is a 0, then that means that x equals a is a solution when f of x equals 0. And that also means that x minus a is a factor, and then that means that if I wanted to write it as an ordered pair, a comma 0 is an x-intercept. So now let's do an example, finding the zeros and taking a look at what the leading coefficient test tells us about this graph. So if I want to find the zeros of this function, sorry, let me grab my pen again. If I want to know the zeros of this function, I'm going to set it equal to 0, and I'm going to actually look for factors. So I'm going to factor out a GCF here. I'm going to factor out a negative 2x squared. It doesn't matter if you take out the negative or not right now, but I'm going to take out the negative, and I'm left with x squared minus 1. When I do that, that actually helps me out because I'm able to see that this is a difference of two squares. So it's x minus 1, x plus 1, with that negative 2x squared out front. So if I'm looking for the zeros of this function, here I'm going to have x equals 0, negative 1, and positive 1. So the ordered pairs would be 0, 0, 1, 0, and negative 1, 0. I also know that my leading coefficient is negative and my degree is even. So that tells me that my arrows are going to look like this. So I have a lot of information about what the graph looks like, and I basically haven't done much work at all yet. So notice how the degree is 4, and I had said previously that you can expect to have 4 zeros. Well, first of all, that's at most 4 zeros. You're not always going to have the number of zeros that the degree is. But we do have this exponent of 2 here that's applied to the x equals 0. That actually means something. Oops, sorry. That actually means that we have a repeated 0. So if you have something that has a repeated 0, hold on 1 second, repeated 0, basically you need to think about what that k value is, what that exponent is. If it's odd, that means that it's going to cross the axes. If it's even, it means that it's going to touch or kind of, you can think of it as bounce on the x-axis. Just scroll down here. So for example, if you have a repeated 0 at x equals 3 with a multiplicity of 4, that word multiplicity means that if this is your 0, the factor is x minus 3. And I'm saying it has a multiplicity of 4, which means it has that exponent of 4. So if you see something like this, where you have an even exponent, that even exponent tells you that it's going to touch, or we can say bounce. The next example says you have a repeated 0 at x equals 4, but that multiplicity is 3. So if that x equals 4 is your 0, then x minus 4 is your factor. The multiplicity, the number of times that it's going to that value occurs, is 3. Since 3 is odd, we know that it's going to cross when the graph reaches x equals 4.